Okay. Now we come to water. Now, I don't have to explain to you the general information about water. You'll know what water is and why we need it and all that. From there, one of the sources of water also you'll know. Correct? I'll just go on to the chemistry part of it. First of all, what is the formula of water? H2O. H2O. And what will be the molecular weight of water? What's the molecular weight of water? 16 mole. 16 mole.
18 U or
18 U or less. He said 16 that one. I said water. So that is 2 plus 16. That is 18. 18 U of grams. Okay. Now, the structure of water. Okay. It is H2O. Now you have got H. All right. 2 of H's on it. So there's another H here. Okay. What happened? He didn't fall now. Now, what is or how many electrons does hydrogen have in the valency shell? You all know that? You all know? The kind of configuration we learned? What is it? How many? 1. So we put here 1, correct? And we put here 1. Okay? 1 each. How much does it need? Don't answer out of 10. How much does it need for stable configuration? 8.
No, 2. 2 8.
2. It needs 2. So it's running short of 1. Correct? Now, in between you have got oxygen. Okay? What is the electronic configuration of how many electrons does oxygen have in its outermost shell, valency shell? 6. So you have got 1, 2, 3, 4, 5, and 6. Okay? This is a pair. This cannot be separated. So it will have to work as a pair. This will have to work as a pair. It's already paired, you can't touch it. This is single, this is single. So now this can be shared. So this goes here, this is shared here. So H has got its 2 now. H has got its 2. Correct? Similarly, this also is going here. So H has got its 2. Correct? And now oxygen has to have, how much does oxygen have for stability?
It's 16, right? No, the atomic number.
What is this boy never paying attention? How much does it need to, how many electrons does it have? It needs to have in its outermost orbital or valency shell.
To be stable, right? 2.
Yeah, how many?
Needs 8.
It needs 8. Okay. Now see how it is the 8. 1, 2, 3, 4, 5, 6, 7, and 8. Correct? So this is your outermost valency electrons for water. That is how you get the binding or the bonding in water. Okay, that's the structure. Now, what we have here now is the importance of water in living things, human beings, animals, plants which are above seawater, above on earth, plants which are underwater, all that is given to you that you can read. Now we talk about the physical properties of water. First of all, water can exist in all the 3 forms: solid, ice, liquid, water, and a gas, which is water vapor, steam, water vapor. Now, the boiling point. Boiling point of water at room temperature or at normal atmospheric pressure. When we say atmospheric pressure, we mean pressure that we are living in, and the pressure outside in the atmosphere and the pressure of the boiling water is the same. Then the boiling point is 100. Then the boiling point is 100. However, as you go higher and higher, when the atmosphere is getting rarer and rarer, and the pressure is becoming rarer and rarer, the boiling point will decrease. Decrease in pressure, decrease in boiling point. Increase in pressure, increase in boiling point. So therefore, when you go up to the mountain side and the pressure is very, very low, water will boil at 100 degrees, but that water is not really giving it at 100 degrees and it is boiled, but the pressure is not there. Okay, it has started boiling even before 100 degrees, it has started boiling. It has to boil at 100 degrees. Even before 100 degrees, the water is boiling. Pressure is low and the water is boiling. So that means if you're taking food to cook, because of low pressure, the cooking temperature of those vegetables also will be low. And when you eat those vegetables, they are not cooked. They are not cooked because the pressure is low. So therefore, you use pressure cookers. You use pressure cookers. So when you put them in a pressure cooker, you increase the pressure, you increase the boiling point, and the food gets cooked very, very well. So when you drink a cup of tea that is prepared higher up, and you drink a cup of tea at ground level, you'll see the difference. That tea is not really boiling, or it has boiled at a very low temperature. The water should boil at 100 degrees. It doesn't reach, even before it reaches 100, the water started boiling because the pressure is low. Okay, so lower the pressure, lower the boiling point. Higher the pressure, higher the boiling point. Okay. Also, let us see the freezing point. Water freezes at 0 degrees centigrade. More the impurities, lower the boiling point, lower the freezing point. Okay, that means if you take pure water, that ice will form at 0 degrees. But if I put salt into that water, salt into that ice will be melted. It will be in the molten state. And it will start freezing at -3, -4, -5 degrees. So more the impurities, lower is the freezing point. Huh? साइन में किया एब्सेंट मारो ना उसको okay lower the more the impurities higher is the freezing point. In other words, lower is the freezing point. That means the freezing point will be -2, -3, -4. That means the freezing point is very, 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 very cold. Is this clear? So that is the formula. That is the principle that is used by the kulfi walas. You know, these kulfi walas are roaming around with a bucket, wooden bucket on their head with kulfi inside. Are they having fridges with them? Are they having deep freezers with them? No, but the temperature of the ice is very, 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 very cold. And that's why your kulfi is very, very hard when he gives it to you. Why? Because he's added salt. He's added salt to that ice. So by adding salt to that ice, he has lowered the freezing point of that ice. The ice is going to freeze at -3 degrees, -4 degrees. So the kulfi is kept at -3, -4 degrees, at the temperature in your fridges. That's why it is nice and hard. Is this clear? So lower the pressure, lower the boiling point. Higher the pressure, higher the boiling point. Okay? Similarly, more the impurities, lower is the freezing point. Okay? More the impurities you add, the more you're going to decrease the freezing point of ice. Okay? Now, what is the density of water? 1. 1. Okay? Now, you know fully well there's something called the anomalous expansion of water. Anomalous means something different, absolutely different. There's an abnormality. What is the abnormality? All substances, when they are solids, okay, they occupy a small space. And when you heat, and when you heat, and when you heat them, they'll expand, they'll expand, they'll expand. And when you take out the temperature, take out the temperature, take out the temperature. In other words, when you cool them, they will contract. In the case of water, when you cool it, okay, it was that occupying that much of space. It like ordinary, simple, common substances will also contract, 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 contract. And as it is contracting and contracting, it's becoming more and more dense because the particles are coming closer and closer to each other. There's still water. It is still water. But the particles are coming closer and closer together. So the water is becoming more and more dense, heavier and heavier and heavier. And it is heaviest or densest at 4 degrees centigrade. Okay? That time you will see little icicles forming. It is half water, half ice. Icicles. And when you still keep on bringing the temperature lower down to 3 and to 2 and to 1, you will find that the water is becoming solid, but it is expanding. And it will expand and expand and expand, okay? Half water, half by ice, till 0 degrees centigrade, when it is a solid block of ice and it starts floating. Because the density has become less. It is expanded. All substances contract and contract and contract. But water, up to 4 degrees, it is contracting. After 4 degrees, it is gradually expanding, becoming ice, expanding, till it becomes solid ice at 0 degrees centigrade. It has expanded maximum, it becomes very light, and it has started floating. That's why either you say, explain the anomalous expansion of water, or why does ice float on water? Same answer, anomalous expansion of water. Or how is it that fishes or sea life is existing even in the very cold temperatures? Because snow is on top and water below, because of the heat around, is nice and warm for them to live comfortably. The ice, because it's snowing outside is solid ice. On top of the water is solid ice, but the ice is floating, but the water below is warm. How do aquatic plants, how does aquatic life thrive during the winter season? Same answer, anomalous expansion of water.
Ma'am, does water show these properties even if there are impurities to it?
If it impurities, no, the temperature will be increasing automatically. Instead of becoming ice, solid ice at 0, it will become solid ice at -1, -2, -3. This is a pure water. What I'm giving you, the parameters I'm giving you are of pure water.
So it won't show the anomalous behavior.
It will show, but it will show at different temperatures. The behavior will remain the same. Impurities only interfere with the boiling point or the melting point or the freezing point. It will not interfere with the physical properties of water. समझ में आया? समझ में आया? Understood now? Now, this is something very important. Latent heat of ice. What's the mean? Latent heat of fusion of ice. What's the mean? Have you understood this? Have you heard of this before?
Yes.
Have you understood it? What have you understood? Tell me.
Latent means hidden.
How? But what happens? Where is it hidden?
So when the boiling point reaches 100 degrees, water reaches 100 degrees, the excess heat which is added is taken by water to change its state. The extra excess energy is taken to change its state.
Did you understand what he said? No? Okay, I'll explain to you very simply. As if there are small KG children. Suppose you take a block of ice. Okay? Now, what am I telling to you is fusion, temperature or latent heat of fusion. Fusion, another word for fusion means what? Fusion means melting. Not like this. No fusing. I didn't say fusing, but it is a you can get the complication. Okay. Fusion in chemistry means melting, fused, melting. So latent heat of fusion or latent heat of melting. Okay. That means what? We're taking water which is solid. Okay. Now in that block of ice, we have put the thermometer. So the bulb of the thermometer is inside the ice. So the bulb will be 0 degrees centigrade. So you will find 0 degrees centigrade on the thermometer. And it will remain 0 degrees centigrade till that ice is ice. Still that water is ice, solid. Now you're heating it, you're heating it, you're heating it. Still the temperature is showing 0. But the ice is melting. What is happening to that ice? That ice is accepting that heat, but is not giving it to the thermometer. It's keeping it to itself and melting. What is that ice doing? It's accepting the heat because it's still heating. But is it giving it to the thermometer so the thermometer thread rises? No, it's keeping it with itself. And when it keeps it with itself, it is making the ice melt. When all the ice has melted and you're still heating, then you find the thread rising. Understood? So that heat which it has kept to itself and refused to give it to the bulb, but it has kept it with itself. And what is it doing with that heat? Ian, what is it doing with that heat? What is ice doing with that heat? It's not giving it to the thermometer. What is it doing with that heat? And doing what with it? It's keeping it with inside and doing what with it? Huh? What is it? Change state means what? I can't understand it in English. Change state means what? Huh?
Inside of the ice.
Huh? Loudly.
Yes, that's the water.
The ice is turning into, it's using that heat to turn into water, to change its state. Once all that state, that solid has disappeared and there's only water, fusion has taken place and then it's releasing it. It doesn't need it anymore. Its work is done, so it is released. That heat, which was not given to the thermometer, but used by it, is called latent heat of fusion. Now, to melt, it needed heat. To solidify, to freeze, it has to give out the same heat. So latent heat of fusion and latent heat of freezing is the same. Latent heat of fusion or latent heat of fusion or latent heat of melting is the same as latent heat of freezing. Only difference is when it has to melt, when it has to fuse, it is taking in heat, taking in heat, taking in heat. But when it has to freeze, it is giving out the same heat that it absorbed. So if there's a cylinder blank, let us say both the heats are the same, melting and freezing. Now we come to vaporization. Okay, vaporization and condensation. Latent heat of condensation and latent heat of vaporization is the same. Water needs heat to vaporize or it has to give out the same heat to condense. Get that concept in your mind clear. What happens is thermometer is in the water and you're heating and you're heating and you're heating and the temperature is rising, 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 rising till of course it has reached 100. You're still heating. You're still heating. The thermometer is stuck to 100 because what is happening? The water is using all that heat to turn into vapor. Once all that vapor, when all that water has evaporated because it has turned into vapor, gone, the thermometer thread will rise. That is called latent heat of vaporization. And then it needed so much of heat to vaporize, and it has to give out the same heat to condense. Okay? Huh? I didn't say they gave the wrong explanation. I asked them, did you understand what he said? They said no. So what I was doing is giving them an explanation, not trying to prove you wrong, you idiot. First class idiot. And he's smiling as if I've given him a big crown of, good qualities. He's smiling away. Like that idiot. When you call him an idiot, he's smiling. He's so happy. His grandmother called him an idiot. Smiling away. All of you are the same. And I am the bigger idiot to come and teach idiots. That is the worst part of it. Or the best part of it. I am a bigger idiot to come and teach you idiots. Yes or no? No. Of course you say no. Then at least you're smart. So now, what is the meaning of specific? Okay. So as I said, that heat that is locked up in that water, in that steam, is not registered on the thermometer. So the thermometer is going to show you only 100, but actually there's hidden heat. Okay, that vapor has a lot of hidden heat. That hidden heat is 540 calories. Meaning what? If the water is 100 degrees centigrade, you put your finger in that hot water, it will not give you as severe a burn as when steam is thrown on your body. Because that heat, that steam has got 100 plus latent heat in it. While hot water has only, if I throw, suppose I throw hot water on you, I'm throwing only 100 degrees temperature on you. But if I throw steam on you, I'm throwing 540 kilocalories of heat on you. That 540 kilocalories is not shown on the thermometer, but you know because I had thrown vapor on you. Water vapor. I mean, steam, not water, sorry. Steam I thrown on you. Steam temperature higher than boiling point. That's all. That's why they say scientific reason. Burn caused by steam is very, very severe as when compared to burn caused by boiling water. Why? Because boiling water, the temperature is only 100 degrees centigrade. But steam, the steam has got 540 kilocalories of hidden or latent heat. Now, what is called specific heat capacity of water? It is that.
How can it throw steam?
How can it grow? No, if you have a kettle and it is boiling and boiling, you put your face there. Do it and show me tomorrow. Put your face there, let the kettle boil, let it boil, let steam come out white, and you put your face there and come tomorrow and show me. I'm not going to go out. I'll come tomorrow and see your face. Kada?
Tomorrow you're on leave.
Huh? I will not. I'll cancel the leave. I will cancel the leave just to see his face. He's trying to challenge me, you idiot. Do it. Foolish fool. Have you understood? A fool is fool. But when I say foolish fool, you can imagine the extent of foolishness that is in your blockhead. Irritating pest. A pest is irritating. But when I say irritating pest, it shows to what extent you're irritating me. Okay, understood now? Have you all followed this now? Why is it that steam burn are more severe than boiling water? Not water, just boiling water, not plain water. Now, what is the meaning of specific heat capacity? It is the amount of heat that is required to raise the temperature of 1 gram of water. 1 gram of water, 1 cc of water. 1 cc weighs 1 gram of water. So it needs the amount of heat that is required to raise the temperature of 1 gram of water from 0 degrees to 1 degree. That much is the heat that is called latent, that is called specific heat capacity. 4.2 joules, 4.2 joules. Okay, that you have to remember. I may have matched the columns. Amount of heat that is required to raise the temperature of 1 gram of water through 1 degree centigrade, from 0 degrees to 1 degree centigrade. Okay. Now, what is meant by universal solvent? What do you understand by universal solvent?
It can dissolve.
Universal solvent, huh?
It can dissolve.
Water
Why?
is,
Why? How?
water is known as
Yeah, but why and how? I'll explain to you. Now, see, pay attention. We say that whenever we put anything into water and we stir it, it dissolves. That is English. In English, we say it dissolves. In chemistry, we say the bonds are breaking. The bonds are breaking and the substance has gone and got into the intermolecular spaces of water. How they went? Because the bonds broke. How the bonds broke? It's because of the special property of the bonds of water. See here, I explained to you here that it's like this. The structure of water is HOH. It's not, show them separate like this to show you the bonding. But the actual structure is H bond OH. Now this bond, hydrogen you know is positive, correct? And OH is negative. Why it got negative? Because oxygen also accepted an electron and this also accepted an electron. Okay? Here hydrogen accepted one electron, correct? But here oxygen also accepted and hydrogen also accepted. So since it accepted this molecule, accepted two electrons, it has got negative charge and this got positive charge. Now, usually when we take two substances and they're sharing, here they're sharing, isn't it sharing? The sharing is absolutely in the center. Absolutely in the center. Equal sharing. Equal sharing. But in this case here, the sharing is not equal because two are taking it and here only one. So the sharing is a little bit unequal. Instead of being in the center, it is unequal. It is pulling it more towards itself. Okay? So therefore, this is becoming negative charge and this is becoming positive charge. So that means this bond has got two charges. Two charges. So it is called dipolar. It's called di means two. Polar means charge. It has got two charges, positive and negative. Now, such a bond is very, 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 very strong. With the result, any substance and every substance put into water, this bond breaks those bonds. Because this bond is stronger than any other bond. Breaks those bonds. Okay? And therefore, that particular substance is said to dissolve in water. Hence, water is called the universal solvent. 99.999% of substances dissolve or their bonds are broken by the water, that is by the HOH bond. Then which other substances whose bond is not broken? That 0.01%, all your organic compounds like petroleum, like fats, like grease, like oils, those bonds are not broken by bond. Their bonds are stronger than this bond. Hence, therefore, they will not break in water. They have got other solvents to break them. That 0.1%, which does not break, are all organic compounds like petroleum, like fats, oils, ghee, okay, diesel, grease. All these, their bonds do not break. They don't dissolve in water. Because their bonds are stronger than the OH, than the HOH bond. Okay, that is why water is called the universal solvent. Now, we know that water is not pure. Okay, and how do we know that the water is not pure? Even your so-called tap water is not very, very pure. How do you know? Can you see the impurities? No. But can you taste the water? Yes. The water is very, very tasty when it is drunk directly from the tap. But water that is drunk from the bottle, mineral water, tastes very different. First of all, you have to remember one thing. The purest form of a liquid is its vapor. The liquid is, say, salty water. It's impure. Now you're heating it. Only the water will get into vapor. The salt will not get into the vapor. The salt will remain down. And the vapor, when you collect it and you cool it, it is absolutely saltless. So that is pure liquid, which you condense. So the purest form of a liquid is its vapor, which you condense and get the liquid back again. The purest form of a solid is a crystal. When you make a crystal, no matter how impure the mother liquor is, meaning the particular solution from where the crystals are formed, when the crystals are formed, they will not pick up the dirt. They will only pick up their own substance and you will get crystal clear solid. The pure form of a solid is its crystal. The pure form of a liquid is its vapor. That is why mineral water tastes very different when compared to ordinary tap water. Ordinary tap water is very, very tasty. Why? Because there are a lot of impurities dissolved in it. Like the bel puri and the pani puri, which your mummy makes at home, will not be as tasty as the pani puri that is given to you by the baya. After he scratched his head and scratched it all over the place and doesn't use those gloves and he's using his hands and his fingers and you are eating it with such relish. Don't make that face. But then we've never eaten from the baya. And then he's put his hands in the shut up! And he put his
Don't eat it from those. I eat some from the stores.
Like
Like Prashant Kaur.
Okay, you know exactly what's happening behind the kitchen. In the kitchen, do you know? Do you know, is that kitchen as clean as your mother's kitchen, you idiot?
I haven't checked.
Huh?
I haven't checked.
You haven't stepped in your mother's kitchen?
In own space.
You go there and you see the difference between your mother's kitchen and that kitchen behind. How they will use their hands. They use the same hand to collect your money or to even punch their mobile. And that same hand they put into the pani puri and it's so tasty. My God, it's so tasty. Because of the dissolved impurities in them. So have you noticed it? Therefore they say that if you want mineral water to have some taste in it, you have to aerate it. You have to aerate it. Okay, when you aerate it, you allow some of the impurity of the air to dissolve in it and the taste will be different. Hot cup of tea, they are aerating it. They're cooling it, at the same time they are aerating it. And that is how it tastes different. Okay? So, what I'm trying to say is, yes, there are impurities no matter how much you have boiled the water. Okay? Or even pass it through the filter. How do you know that there is impurity in the water? They have said, take tap water, take it in a saucer, a white saucer, okay? So white saucer has got water in it, and you place that water over a beaker which contains water. So there's a beaker, it's filled with water, and on top of it you have gone and kept this saucer, which has got the water coming from the tap. And that water coming from the tap, that water is under experimentation. Then you keep on heating the beaker. The beaker will keep on giving out vapor, correct? It's boiling. And as it is boiling, the water in the saucer is evaporating. It will evaporate and evaporate and evaporate. And when every drop of water has evaporated, you take that saucer, you keep it down, and you will see rings on that surface of that saucer. Each ring is telling you the presence of impurities in the water. This is clear? That is how you prove that water that you drink is not pure. Okay? Now, secondly, how will you prove that water has got dissolved gases in it? Dissolved gases in it. Now, can you see? If you can open up your book, you see the diagram in the book. Open up your book. Can you see the diagram? Can you see the diagram? What about Dalal? No. Turn over. Oh, you don't have the diagram. Alright? You have paid full money for the book.
Yes.
Then how come you get only half the diagrams and other Dalal? This one has got all the diagrams. See here.
Which is this?
Mine is an old book. There, if you turn the
Page number
pages.
42.
Dalal. What about Dalal? Dalal doesn't have it. Dalal doesn't have it. Now here, for the benefit of those who don't have it, I'll draw a small diagram for you. Okay? Now see here. There is a round bottom flask. A round bottom flask. And it is filled with water. Filled with water. It is completely filled with water. Okay? completely filled with water. And it is being heated. It is being heated. Now, there is a delivery tube that goes into a beehive arrangement. And on top of it is a gas jar. And this is also filled with water. Completely filled with water. Completely filled with water. Completely filled with water. Now what happens is, as the water is boiling, the gases come out. Bubbles, 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 bubbling through. And what happens is, this level of water is dropping down and the bubbles are passing higher up. Now, each bubble is a bubble of a different gas, which is present here. And each bubble has got vapor, hot. This is hot now. This is hot. So it's got vapor covering it. But when that bubble comes here in contact with cold water, the cold water condenses and only the dry gas is collecting upwards. So this will come, this level of water will come down and this is all filled with gas. Okay? When you take out this gas and you test it, it's about 33% of oxygen, 66% of nitrogen, and whatever is left behind, 1% or something of nitrogen. That shows that these are the main three gases that are soluble in water. Okay? 66, 32, 1%. Pardon me? The gas will not condense. The vapor, water vapor, that way. Okay? So their condensation temperature is very different. Each gas has got different temperatures for cooling. Huh? All right? So that is it. So now see there. So what is the importance of water or air dissolved in water? What is the importance of
Oxygen to the marine life.
It gives oxygen to the marine life, okay? Fish and fish and plants also are thriving because of that water. Then what else? You have got the formation of photosynthesis taking place underwater. Photosynthesis there taking place underwater. Then also you have got carbon dioxide there dissolving in the water, forming carbonates. Okay, forming carbonates. Those carbonates are then further converted into bicarbonates. Bicarbonates. And the shellfish, they keep on absorbing the calcium from the calcium bicarbonate to form layers and layers of their shell. This way, they form the shell from the carbon dioxide, which is present in the air, which is present in the water. Okay, as I said, water contains oxygen, carbon dioxide, and nitrogen. Okay, 66% of carbon dioxide used for photosynthesis, used for marine life, and also used for the formation of their shell to cover their soft bodies. Okay, that's all. Now read. Come on, read carefully. Are you able to understand my explanation? Problem? You want to go to sleep? Pack up your bag and go home.
No, something in the,
Huh?
something went into
Something went into?
your man.
Next time you please say that you have your own textbook. I won't accept any excuse. Hey, what is the matter with both of you? What did I ask you to do? Read your book now. That Dalal has got nothing, take this book and read it. How many of you are following Dalal? If you got Salima, huh? Bring the book here. You sit and read from book because Dalal doesn't have what I explained to you. This is your school. And there's one directly for solutions. There's one directly for solution. They're not explained to you whatever I explained to you. They're not given to you. They will need the vaporization, all that, nothing from to you. How are you able to understand what I explained to you? My God. Finish your book, chapter's over. I would suggest you buy a second-hand Selena book and read. Selena is very, very informative. Those who've got Selena, share it with those who've got Dalal. I don't want to see the Dalal in the, because it was contained, all what I told you and explained to you, is not there in Dalal. You have not done this chapter in the school also, no? Read. What book have you got? Selena.
Same school.
Okay. There was one girl Ria in your school, no?
Ria?
Ria.
Yes. Yeah.
How is she?
She's great.
Ria Anchan.
Anchan, yeah.
How is she?
She's in 11th now.
Yeah, that's it.
She's good at singing and art. More stuff.
What's the matter? Well, your book is behind, is it? Or in front of you? Look, you should put somebody who has the last, who has Selena. You are not done the session in the school also. No? But in the first chapter, everything is using Dalal. So she uses only that much from the Dalal. But so much extra that she does. And usually takes from English book.
Ma'am, she can sing. Yes.
So this fellow doesn't want to study and neither will he let her study, and she's a very studious girl. So let her study on her own. She knows exactly what to do. That fellow is a living devil.
Sorry.
Don't look at me like that. I'm not backing up your big eyes. Have you got the volume? Did you get the volume? You were absent last time.
I have it, but I don't have it.
Yeah, then you see what, how much is there. If it's, you got the volume? Yeah. Now you can read from the volume. Volume is there. Yeah, everything is here. Look from here. Okay. Yeah, it's okay. Yeah. Yes. You can read from the volume. Take it. If you don't have Dalal, learn from the volume. UT volume is everything.
And what is the dielectric constant?
Dielectric constant is the same thing like this, no? As I said, diet, having two, but then don't bother about it. That is not necessary. Water.
It is
Yeah, but it is not there in your course. Sometimes something extra given to you which is not wanted. It's dipolar. Same thing as dipolar. Remember I told you dipolar on the board? That's the same thing, dielectric constant of water, having two charges. Where did you read it? What page?
Page number 41.
Give me that.
About that big yellow box.
It's actually dipolar. Dielectric means dipolar. Same thing. Polar is charge. Electricity is charge. Karachin. Start the question answers. Now, are you talking and laughing? Which part of chemistry is making you laugh? Huh? You want to go home? Go home. Pack up your books and go home.
हेलो गाइस, तो अभी हम लोग एक ज्वेलरी शॉप
Give him one knock on his head. One knock on his head. Hey! What is your brother doing now? Ask him to come and meet me one day. I want to see him. Does he remember me?
Yes.
Yes. Really, next time you don't come to my class, okay? If you're you want to laugh, you can do as much as you want to laugh on the roads or in your own house. Don't come to my class and laugh. Okay, you can pack up. Yeah, sit down and Nancy, sit down. Tomorrow, what will you have then? You will have a holiday or some other?
Holiday.
No, some other teacher will come.
No, no, sir. Priya
Oh,
told
is it now?
Priya told us.
Is it like some other teachers want to come?
Yeah, because I don't even want to waste. I don't know. Huh?
But
When
because she usually comes on Saturday.
she comes, but she goes for CBSE, no?
Chalo.